So here we go for the first problem, which is telling us that a large open top container of negligible mass and uniform cross-sectional area A has a small hole of cross-sectional area A upon 100 in its side wall near the bottom. The container is kept on a smooth horizontal floor and contains a liquid of density rho and mass m0. Assuming that the liquid starts flowing out horizontally through the hole at time t is equal to 0, calculate the acceleration of the container, and in part B, speed of a flux when 75% of liquid has drained out. So let us draw a figure to understand the situation of the problem. Here is a smooth horizontal floor, and on it we place this large open top container with a small hole at near the bottom that is kept initially closed. And they have set some dimensions here. The cross-sectional area of this container is taken to be A, while the cross-section of this tiny hole is taken to be, I'll be considering it this A1, I'll be calling it this is A, and the cross-sectional area of the hole I'll call it A2, and which is given to be A upon 100. Is further given that when you fill it up with a liquid, for this liquid density is rho and the initial mass, this I must write separately because I am showing you a situation where the liquid has already started draining out. It started at time t is equal to 0, and I am showing liquid is coming out horizontally through this hole at the bottom, and I am just drawing here an intermediate situation. As the liquid flows out through the bottom, the level of liquid starts falling from its initial level, and we consider any intermediate instant when the height of liquid column standing in the container is a variable quantity y. We shall choose at the level of the floor, that is to the bottom of this container, I shall take y is equal to 0, and gravitational potential energy for the liquid will be taken to be 0 at this level for convenience. Now, as a first step to find out acceleration of the container, we must find out the speed of a flux. I just show here with this arrow, you understand this blue arrow. This is the speed of a flux coming out, and it's common sense that if this ground, if this floor is frictionless, that is frictional coefficient is 0, this motion of liquid through the bottom in the direction to the right in my figure will induce a simultaneous motion of this massless container towards the left in my figure. So I might use another arrow to show the velocity of the container with the residual liquid as an effect of liquid coming out towards the right to this bottom hole. And first job is to find out the speed I'll be taking here. Well, let me take 2 points before I apply the Bernoulli's principle. I shall take 1.1 at the free surface of the liquid in this intermediate step, and another 0.2 at the mouth of this hole. That point is called the point number 2. And according to Bernoulli's principle, for an ideal fluid in steady flow, the sum of pressure, kinetic energy per unit volume, and gravitational potential energy per unit volume remains constant along a streamline. So, since I choose these 2 points, one at the free surface, another at the mouth of this opening, we might write down for the point 1, it is P1 plus half into rho into V1 square plus rho into G into Y1. This sum must be equal to the similar quantities addition. We just add them up for the point 2 here. That is P2 plus half into rho into V2 square plus rho into G into Y2. You are familiar with these different symbols. P is the pressure, rho is density. V1 and V2 are the speeds of this liquid at points 1 and 2 respectively. G is the free fall acceleration. Y1 and Y2 are the respective heights of these points 1 and 2 above the reference plane. So you can put the values now one by one. For the point 1, at the free surface, pressure is atmospheric, PA, plus half into rho into V1 square. I assume that speed of the liquid as it goes down is V1 at this point. The height above the reference level, that is taken to be Y. So I have got plus rho into G into Y is equal to, once again, for point 2, open to the atmosphere, pressure is atmospheric, plus half into rho into V2 square. That is this speed of the flux as it comes out. I am calling it a vector V2 here. Okay. Plus, what about this potential energy term? This whole is taken at the bottom level. Therefore, the value of Y2 is 0. And this term simply vanishes. Also, atmospheric pressure terms cancels out. And you are left with, as you can see, rho into G into Y is coming out to be half into rho inside bracket V2 square minus V1 square. I can get rid of this rho term as well, density of the liquid, and this is giving me 2 into Gy is equal to V2 square minus V1 square. Let us pause for a moment and see if we can get rid of this V1 term also. You know by equation of continuity that since it's a steady flow of an ideal fluid, therefore the volume flow rate must be the same at both points 1 and 2, and volume flow rate, that is dV dt, this is capital V for volume, is given by the product of cross-sectional area and the liquid speed at any point. So at point 1, this is the product A1 into V1. At point 2, this is the product A2 into V2. And it follows therefore that the ratio V1 by V2 is coming out to be A2 by A1, right? Now A2 is the cross-sectional area of the hole given to be A upon 100, and A1 is the cross-sectional area of the cylindrical tank that is given by A. Therefore, putting the values, this is A upon 100 divided by A, A's cancel out. This is 1 upon 100, a very small value, much less than 1. It only shows that the value of V1 is negligibly smaller than the value of V2. When you have got a large tank, compared to the speed of flux, the speed of liquid here is very small. We might ignore it in the expression, and if I call equation number 1, this equation number 1 can be approximated without any significant error to be 2 into Gy. That is coming out to be V2 square. Now what does it mean?
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.